Okay, I think we're live. See anybody? Here we go. Okay. All right, so I see the chat now. We've got some people here. That's great. Welcome to the December live stream. I know it's a bit early. We would normally wait till like next week, but next week is Christmas. I didn't want that to mess with anybody, so we're going with the 18th. So welcome. We got some good questions today. I think we'll have a good time. All right. So let's see here. Oh, hey, looks like everybody can see me. That's great news. All right. Okay, so as usual, we're going to start with the $10 and up questions, and then we'll go from there. It looks like we've got a good turnout, so I'm hoping for some great conversation today. All right, so first, Marino Hernandez wants to, let's see, if photons are being absorbed and re-emitted each time they collide into stuff on their journey from the core of the sun to its surface, do the re-emitters remember the light spectral line info? The photons take about 100,000 years to get out. Okay, I see where your confusion is. All right, Marino. First of all, the spectral lines of the light, the ones that we see when we look at the sun to tell what it's made of, aren't made inside the core of the sun. The photons are, but the lines that we see aren't. And this is not something that gets talked about a lot. You usually hear, oh, well, we looked at the spectral lines and then we know what the stars are made of, and then people move on. And it's a very quick explanation, but it's a little more complicated than that. Go figure. First of all, when we look at the solar spectrum, we are not seeing light from the core of the sun. We are seeing light from the surface of the sun. The surface being the photosphere, I think is technically the name of it. All right, so there's this, there's, obviously the sun has multiple layers in it, but the very top layers, excluding the big corona that's on the outside, we'll talk about that in a sec. The actual outer surfaces that you would see, anything you would consider to be a surface, would be the chromosphere and the photosphere. And the chromosphere, it just means color sphere. And so that is primarily where the color of the sun comes from. And so the chromosphere is what we're receiving the solar spectrum from. That's the layer that we're receiving it from, and it's on the outside. At the very, very bottom of the chromosphere is something we call the photosphere, which is the boundary where the plasma that the sun is made of is no longer transparent at all, right? So there's this thin layer of plasma that we can see, but you can still kind of see through it. It's kind of translucent. Whereas once you get to the photosphere, that's it. You can't see any deeper than the photosphere. And so, below that, the density of the plasma is just too much, and the photons get trapped and bounce around and lose energy. And that's true all the way down to the core, which is why it takes tens of thousands or hundreds of thousands of years for photons to actually get out of the sun. And so the vast majority of the light that we receive from the sun comes from the chromosphere, the outer layer, which is a very thin layer, relatively speaking. And so we don't have any direct evidence for the interior of the sun. Only what the surface it has. So like when we look at the, and I guess before we get into that, the second thing I want to mention is that the spectral lines we see are not emission lines like you would get from one of those glass tubes that they always pull out in, astronomy classes and stuff. What we see when we look at the sun is actually absorption spectral, absorption lines. And so the most of the light emitted from the sun is in the form of thermal radiation, not atomic radiation, not atomic spectral lines being emitted. It's just thermal radiation because the outer layer of the sun is hot, right? It's about 5,000-ish, 5,500 degrees. I should say 5,500 Kelvin. It's not degrees. And so it's just a thermal spectrum. It's a black body curve. But when we look at it, we actually see these dark lines in that full visible spectrum. We see a bunch of dark lines in it, and those dark lines tell us that when those photons leave the chromosphere, they leave that outer layer of the sun, some of their energy is absorbed by atoms in the rest of the chromosphere or in the corona, which is even further out. It's basically the sun's atmosphere. And so what we can see from the spectrum is absorption lines, energy being absorbed. And so what that tells us is the composition of the chromosphere and the corona. It does not tell us the composition of the inner layers, like the radiative zone and the convection zone and the core. Those sorts of things and the behavior of those inner layers we have to infer from the information we have on the surface and from, plasma and nuclear physics. So we don't have direct access to that information because it's below the photosphere. It's below a layer that we can't see through. Hopefully that clears some things up. All right. Hugh Arthur is wondering, it says in the comments of a previous video, I asked a question about how entangled pairs work with these state vectors. Right. So at the end of November, I released a video on quantum superposition. I'm sure you've all seen it. And I got several questions from several people, including Hugh, about how entanglement works with these state vector things that I was talking about. And it's actually not that complicated, right? In fact, here he says that I said that the entangled pair exists as a single state together, but he was looking for some clarification. So, in the video, I talk about just sort of a hypothetical abstract state of roughness, right? There's rough and smooth. And then you can have superposition, some combination of those two states. And so in a entanglement, you wouldn't just have one word inside of the bracket. You would have two, one for each of the particles. And I'm actually going to do a little screen share here. So we're going to screen share. Woo, infinity. And we're going to take a look at this. Now, this is a screenshot I took from a Looking Glass Universe video. Mithana does great work. You should check her stuff out. She hasn't posted in a while. I've been meaning to check in and make sure she's okay, but I know she was trying to finish up a PhD, so she probably just got busy. Anyway, this is, aside from some missing coefficients, she was trying to keep things simple. This is what an entangled superposition would look like. You can see that you've got essentially an electron and a positron, and both of them are inside of the state, right? Whereas if this was just the state of an electron, you would just have a blue circle inside of this bracket and a blue circle inside of this bracket, and it would be, one would be spin up and one would be spin down, because my smooth, rough states are just metaphors for quantum spin. But if you have a pair of particles that are entangled, like this electron and positron, then you're going to end up having one state bracket that's got both particles in it. The particles exist together. It's impossible, as she says here, it's impossible to describe, right, the state of one of the particles without the other. And so the state vectors include both particles at the same time. And so you end up with the electron being spin up, then we know the positron is spin down, and then this other state is vice versa. And you can have superpositions of those vectors as well, right? But these two vectors here would be the basis states for the vector space describing this entangled pair. And so it isn't that much of a stretch beyond what I was talking about in that video, and I'm sure I'll do a follow-up about entanglement at some point. But this is essentially how this works. Okay. All right, and we're back. So hopefully, Hugh, that answers your questions about entanglement there. All right. Warren, who I also see in the chat, says, I was taught in chemistry that reactions like rusting and burning release energy because the reactants, reagents have more energy than the products of their chemical reaction. Sure. So we're talking, exothermic reactions versus endothermic reactions, releasing energy versus absorbing energy. And so the question is, different reactions seem to produce different amounts of energy, even though they take in the same reagents. Like when, okay, so there's some discussion of ATP molecules, which is a biology thing. Talked about it a few times. What are the different amounts of energy based on? Is there a standard baseline against what we measure reactions? Well, so I guess just to clarify, right? Essentially what you've got is you've got two situations to consider before the reaction and after the reaction. And you want to consider the molecules that you have in both situations. And so you consider all the potential and kinetic energy you have before a reaction takes place inside the molecules that exist. And all the potential and kinetic energy you have in the molecules that exist after the reaction. And in order to determine whether or not they're exothermic or endothermic, you just subtract the two numbers, right? So if you say, usually it's final minus initial. So if you say final minus initial is positive, then what you have is an endothermic reaction. The molecules, the particles have absorbed energy from their environment, whereas the reverse is the case for a negative situation. That would be an exothermic, right? You've released energy. Now, what that usually refers to is heat, right? So instead of the energy being contained in like potential energy, it's contained in kinetic, the wiggles and jiggles of the molecules. That is different than talking about ATP molecules, because ATP molecules don't represent heat like the wiggling and jiggling of the atoms. They can contain that, but that's not what we talk about when we talk about the energy in an ATP molecule. We're talking about potential energy in that case. We have energy holding one of the phosphates, right? The TP is a triphosphate, so there's a third phosphate shoved on the end of that molecule. And it's fairly loose, but it's sitting there, and the fact that it's there is holding some energy, energy that can get used later. And so it's not exactly the same thing as heat. I feel like I'm not really actually answering your question here, but what kind of reaction happens is going to depend on what molecules are present and what the conditions of the environment are, right? And so if you've got one reaction here, you say produces 30 ATP molecules and another one only produces 2, What's the difference? And there are a few factors at play. One of them is the obvious factor, which would be what kind of molecules are present, right? And in what proportions. And so if you've got um, some different molecules in there, maybe you have some kind of like catalyst or something, it can change the chemical reaction. It will be different. But you seem to be suggesting that the same molecules are involved, at which point the other major factor would be the environment, right? How much energy is there available for it to absorb? How much heat is available to be absorbed in the reaction? And, different things can happen depending on whether there's a little bit or a lot. And these sorts of things can control the rate at which the reaction occurs, and also whether or not it occurs. And so it's, again, reality is complicated, but that's essentially what's going on there, right? So if it seems like the situation is the same when you're looking at some kind of chemical equation that's been balanced, the reason it looks like it's the same situation in both cases is because something's being ignored. It's very common for seasoned chemists to leave things out of chemical equations. Because they're just kind of implied or assumed or something. If another seasoned chemist is reading the equation, they're going to know what the situation is, and they're not going to have to worry about having those extra things in there. But there are always, like, I shouldn't say always, there are often other molecules involved in a reaction that are not included in the actual balancing that's being done. And those other molecules can affect what happens. All right, one more, and then we open it up to the chat. Christopher Bennett says, most science explainer books I've come across give a decent, in my non-professional opinion, explanation of the fundamental forces until they get to the weak force, where they inevitably wave their hands and say that it mediates radioactivity. And that's the last you hear of it. And then there's some information in here, but it says, how exactly does the weak force work in the Standard Model? I think I have an interesting answer for this. First, I can understand your reaction to how the weak force is usually explained. And that is because of the way the forces actually work. So it seems, when they actually explain it, it seems like they're not really giving the weak force the attention it deserves. And I guess on some level they kind of are, but it seems way worse than it actually is. And so a lot of the misconception stems from how we think of the word force, right? And why the word force shouldn't actually be used here. So when we think about gravity, for example, we can say, oh, well, gravity is attractive. And then we can look at electromagnetism and we can say, okay, well, electromagnetism can be attractive and repulsive depending on the situation, right? And then we look at the strong nuclear force and we say, oh, well, that's binding particles together in a nucleus. That's kind of like an attraction. And then you get to the weak force and you're like, wait, it's not really attractive or repulsive, but like it is kind of mediating this thing. So, I mean, I guess we can call it a force. And so like it gets really iffy, right? It sounds wishy-washy, and it only sounds wishy-washy because we're thinking about this wrong. So you don't want to think of these fundamental forces, and I'm using air quotes for a reason. You don't want to think of them as attractive or repulsive like we would think of a force. These things are not forces. They're not the fundamental forces, they're the fundamental interactions. The word interaction is very important here. In classical physics, like Newtonian physics, they're basically the same thing. An interaction and a force is the same thing. But when you're talking about quantum mechanics or quantum field theory, they're not. In fact, the entire concept of a force is it's not very useful in the quantum realm. It's not something that gets us anywhere. And so when they say that the weak force, mediates radioactivity, like that's basically all it does. But it doesn't make it lesser than the other forces, other than the fact that it's weak. It just sort of highlights the fact that these interactions are not actually forces. They're just particle interactions. Energy and momentum is being exchanged between, quantum fields, and those energy exchanges look like particles. And in the process of those, what we call like nuclear reactions or, particle reactions, the particles that we see in those fields can change. They can change behaviors and change types and all sorts of stuff. So, what happens with the weak nuclear interaction, and I'm hoping to get into this in more detail in a future video, maybe this year, fingers crossed, is that essentially there's this weak field, or like multiple weak fields, depending on how you want to count the fields. But there are quantum fields that we refer to as the weak field. And in that field, 3 particles are possible. We've got W plus particles, W minus particles, and Z0 particles, right? So each of those things, they have different amounts of mass and different types of charge, right? So the plus, minus, and 0 tells you what kind of charge it is: positive charge, negative charge, or 0 charge. And what that electric charge does is it tells you that particles in the weak field can interact with the electromagnetic field, because they have electric charge. That's what electric charge is. It tells you that there's a link there. There's an interaction, right? And everything that happens in quantum field theory is all about interactions between these fields. Everything, literally everything. It just so happens that the other 3 interactions, potentially gravity, but not yet, electromagnetism and strong force particularly, are interactions just like the weak interaction, but those 2 forces, EM and strong, they can also be conceptualized classically, whereas the weak interaction cannot. The weak interaction is a purely quantum mechanical, quantum field interaction, and that's all it is. And there's really no other way to imagine it. There's no way to imagine that interaction on a classical level. And so it's a conceptual boundary, not an explanation boundary, I guess is what I'm getting at. And so essentially what it does, what these weak fields do, is they allow certain interactions to take place. So they allow quarks, for example, one like an up quark to decay into a down quark, which allows a proton to decay into a neutron. So there are these reactions, these fundamental particle interactions that become available because the weak field exists. And so the energy is transferred. The energy from, say, an up quark is transferred into one of the weak fields. And then the weak field particle can travel for a bit, and then because it interacts with other fields like the electromagnetic field due to its charge, it can release that energy into that field or the neutrino field or whatever, right? There are interactions. And so that's sort of all particle physics is about. It's about figuring out how these interactions take place, and weak fields make certain interactions possible. I hope that answers your question. Um, okay. So on that note, looks like we have an active chat here. Let's open it up. Do, 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 do. Let's see. So if we were to precisely account for everything in a reaction, then the input and output would be perfectly balanced every time, but we ignore stuff sometimes, and that's why it looks different. Yes, that's what I'm saying. There may be something I am unaware of chemically that is also at play there, but I bet that's like 95% of the problem is that things aren't getting included. Let's see. Trevin says, I've been hearing from some videos like the latest one from Fermilab how a slight imbalance in the creation of matter versus antimatter resulted in matter coming to dominate the universe. Yes, I'm actually working on a video about this exact topic. But yeah, so we may not be able to tell directly whether or not a galaxy that we're looking at is made of matter or antimatter. And so originally, because we couldn't tell, there was a whole group of scientists who felt like, well, maybe half the galaxies out there are antimatter galaxies, and then that takes care of it. The matter and antimatter is balanced. But the problem with that is that when you actually put that in the context of, the Big Bang model that we have, it doesn't really add up. Out of context, it makes sense as an argument, but any argument that gets made has to be put in the broader context. And this is actually an issue that we have with a lot of things, right? People look at dark matter and they're like, oh, well, dark matter, there are plenty of other explanations for that stuff. But the problem is that your other explanations don't fit in the broader context. And dark matter does, right? The broader context is very, very important. And so when you take the idea that, well, maybe some of the galaxies are antimatter and you put them in the broader cosmological context, it doesn't make sense because we can track things backward, right? And we can see that in order for example, the cosmic microwave background to be as uniform as it is, all of the particles, all of the matter and whatever antimatter there was had to be way too close together for it to be possible, right? They were all these particles were way too close together for too long, and by too long I mean a very large, tiny fraction of a second, right? And I know that sounds like an oxymoron, but there's one tiny fraction of a second, a small one where, if the particles got far enough apart, then antimatter galaxies would be possible. But then it turns out that when we put this information into our models, we find that it was actually this long, right? So it's instead of this long, they were together this long, and that's just too long. And so in that extra bit amount of time, all of the matter antimatter would have reacted together. You would have had a matter antimatter reactions happening all over the universe, and all of those particles would have been turned into photons. And those photons are the photons that bounce around and get absorbed and re-emitted, and ultimately became the cosmic microwave background. And so the particles were together in the early universe long enough that all of the matter-antimatter reactions that were going to take place naturally took place, essentially. The vast majority of them. And in a perfectly balanced universe, in a perfectly balanced matter-antimatter universe, that should have resulted in a universe that was just full of photons and basically no matter at all. And well, we can see that that's not the case. You know, you and me, we're all made of actual particles. We're all made of what we consider regular matter. And so the only thing we can conclude there is that there was an imbalance at some point, right? We had an uneven, an unbalanced amount of matter versus antimatter, and that put matter in the favoring spot. There was just a little bit more matter than antimatter. Not much, right? When we look out there, we see about 10 to the 80. We estimate there are about 10 to the 80 baryons. Let's say baryons are like protons and neutrons and stuff. So we call it baryonic matter. And so there are about 10 to the 80 regular matter particles in the universe, which is a lot, right? But when we do the same estimate, we find that there are 10 to the 89 photons. And remember that only seems like 9 more, but it's 9 more in the exponent, which means it's a billion times more. 9 more powers of 10 is a billion. And so there are 1 billion times as many photons in the universe as there are matter particles, which is a lot. This is also another video I want to do on explain how those estimates are actually made and stuff, which I can't really cover in a live stream. But the idea there is that if you actually work the math out there, what that's saying is that for every billion matter particles and every billion antimatter particles, there was 1 more matter particle, just 1. And that 1 little extra matter particle for every 1 billion particles was enough to give us the universe full of matter today, which is insane. And so we know that that's the case because we see it. We can see it in our universe. The issue is we're not sure exactly how that happened. We're not sure what mechanism actually caused the imbalance. We do have some ideas, which I'm going to save for an upcoming video that I actually had to, I had someone research for me. But there are some explanations for why it might have happened, but we're not entirely sure. It is an active area of research at the moment. I love cosmology stuff. I could sit and talk about this for hours. Okay. So we got some people answering each other's questions. See, Tommy wants to know, could you explain or simplify gravitational vacuum polarization, which makes Hawking radiation possible? I'm not sure exactly what you're asking. I don't think I've heard that term before. I'm not sure what vacuum polarization could mean. Polarization means different things in different contexts, even in physics, and so it can get real confusing. When I see polarization, I tend to think of light photon polarization, but generally polarization just means that there's some directional preference. And so it means a lot of different things. I'm not sure how the vacuum could have a directional preference or how that's related to Hawking radiation. The things that I've read about Hawking radiation don't involve gravitational vacuum anything. I mean, technically it's particles coming out of a vacuum, but it's kind of hard to know exactly what makes Hawking radiation possible because we don't have a theory of everything. just put that in quotes, theory of everything. And so even when Stephen Hawking was, predicting Hawking radiation, what we now call Hawking radiation, he couldn't figure out the mechanism. There's a Bogolubov transformation that he used. It's just a mathematical tool, but he used it to kind of bypass having to have gravity unified with the other forces. And as a result, though, it predicts Hawking radiation without having to know what the exact mechanism is. And so we don't actually know what makes Hawking radiation possible. I know that there are some scientists, some physicists working on explaining it with quantum tunneling, that particles could maybe quantum tunnel through the event horizon from the inside. And that looks kind of promising, but it's not really finalized yet. It isn't a solid argument. And so I guess the less satisfying answer to your question, Tommy, is that we don't really know what makes Hawking radiation possible. And that's kind of where we're at with that. See, I'm a newbie and not much versed in the ways of natural science, so my question might be simple or even weird. So I wonder, is there possibly more stuff to the left and the right of the EM spectrum that there may have not detected yet? No. And so technically, like when you look at an EM spectrum, it looks like this finite bar. But it only looks like that because the scales that go either direction on the bar, on the little bar graph thing, are exponential. And so because they are exponential, it takes an infinitely long spectrum and compresses it into a finite length visually. And so every single possible frequency and every single possible wavelength is on that bar. It just turns out that the ends are crammed closer and closer and closer together, right? And so we get a really good view of what the middle looks like. And then when you get, near the end, things get a little cramped. Where, each of the spectrums sort of approach zero. But that's something that doesn't really get talked about very much. And so people get the impression that there's this like finite range, and it's not. It's an infinite range of wavelengths and frequencies. So everything is accounted for, right? So anything below a certain amount on one end is considered a radio frequency all the way down. And then anything above a certain amount is considered a gamma ray all the way up. And there's really no room for there to be anything else. It's a great question, though. Do you wish educational videos, books, etc. would spend more time explaining why we know something instead of just explaining the thing and moving on? Yes and no. I mean, I don't explain that. I don't explain why we know something every single time either. It depends on the need of the situation, right? So, each topic that you're trying to cover, you have a goal, right? You have to come up with a goal, like what's my audience? What do I want people to get out of this? And if there's something very specific, something, focused that you want people to get out of it, droning on about why we know something can distract from the main point. And so I think it just depends. It depends on the situation. I think that's as far as videos go. I mean, as far as books go, I think that books can get away with it a lot more. You can include all the information in there, and if people don't want to read it, they don't have to read it. But I think it would be something valuable to have in the book. But there, you also run into the trouble of like textbooks. Because while it would be useful for people to know, and I think that it would put what they're learning in the right context and sort of tell a story, you also want the book to be useful, and you want the book to be as cheap as possible. And the more you put in a book, the thicker it gets, and the more expensive it is to print, and the more the markup's going to be, and the more it's going to cost students and stuff. And so, there's a practical aspect to it. And so, again, it depends. But I think in books, you can get away with it more than you can in videos, which is why I kind of leaned into that in my own book. But yeah, I think more. It would be nice if more channels, more pure education channels covered that stuff. But I also know that those videos don't actually perform very well, right? So you can make those videos, but they're not necessarily going to appeal to the larger audience. They're just going to be for your core, which is good, but you can't necessarily do that every single time. See, how many times have you had to explain that putting a generator on a wheel of an electric car won't improve the range or make it charge itself while driving? I've never had to explain this before, but I think it's because no one's actually brought it up. No one's actually asked me the question. And so I think to make matters worse, hybrid cars will, they do that a little bit, where the generators on the wheels charge the battery a bit. But that's because they also have, the extra fuel source. Whereas electric cars doesn't really work because it's all electrical, and so putting a generator on the wheel isn't going to do anything. But because you still need energy from the outside. I guess I'm explaining this, but I've never actually had to explain it to anyone. But I am prepared. I am prepared to explain it. See, Tommy wants to know, do you prefer inflationary models of cosmology over the Big Bang model with initial singularity before the inflation? Well, I would consider inflationary models also Big Bang models. Big Bang, the term Big Bang is kind of a large umbrella. It includes a lot of different things. It's a big tent, right? Metaphorical tent. And inflationary models are just examples of kind of Big Bang model. But I think what you're referring to here is the eternal inflation, and you're trying to contrast that from the, so you're trying to contrast basically the infinite past versus the finite past. And those are certainly two different categories of Big Bang models. I don't know if I have a preference. I try to, obviously there are aspects that I like, but I don't think that I have a preference that's really biasing anything, because opinions about the very, very early universe, they don't really affect anything at the moment, because our models don't go back that far anyway. And so at this point, they're just opinions. But I like the idea of there being an eternal past and an eternal future, but that's just a personal opinion. It's a personal feeling. But it doesn't affect my, my ability to look at the actual data and the models that we have, critically, with a clear head, because those models only go back so far, and what they go back and tell us, everyone agrees on, right? It's the stuff before the models where things get a little muddy. It's muddy territory. And of course I have an opinion. I am a human being, but I like the idea of an infinite past, but I don't know that it actually works. But to clarify, though, uh, very few people consider the initial Big Bang singularity to be a real thing. Just like very few, I should say, very few physicists, just like very few physicists consider a black hole singularity to be a real thing. The same goes for Big Bang models, right? A singularity is just a point where our model blows up to infinity, or where our model stops working. Or a better way to say that, a more accurate way to say that is, if our models have places that blow up to infinity, places or times in this case, then at some point before we get there, as we approach that infinite boundary, right? We know that at some point before that, as we're approaching it, our model fails, and we don't know exactly where it fails, but we're all pretty sure it doesn't work all the way to, and then infinity it stops working, right? It's not like that, right? It just means that at some point in approaching that infinite value, our models stop being accurate. They stopped actually matching the universe. And so that works with singularities inside black holes, and that works with the initial singularity of the universe, right? We have this early universe where if we track things back, we see this moment, this time of infinite density, which makes no sense and shouldn't happen. And so we have to come up with some way to resolve that. We have to fix the model, and models like eternal inflation models solve that problem by saying, oh, well, it doesn't ever quite get to infinity, right? It's kind of the cheap way out, I guess, but they are conceptually appealing. Let's see here. 10 to the 80 matter, and who would know the size of the visible universe and powers of 10? And what unit? Depends on the unit, right? I mean, we're talking light years. The size of the observable universe would be, what is it, 93 billion light years across as diameter? It's big. But it's not 10 to the 80 big. It's just 10s, 10 to the 10-ish, not 10 to the 80. So 10 to the 80 is a lot of particles. Warren says, are the fundamental forces completely independent of each other, or do they influence each other's behavior? I don't know if I'm qualified to answer this question. I think, there are interactions. Like I was saying earlier, the weak fields interact with the electromagnetic field, and so there is a direct interaction between those fields. The fields that facilitate specific interactions can interact with each other. And so I think they are not completely independent. And I know that we have, unified models, right? We have something called the electroweak model, which unifies electromagnetism with weak force. And that makes sense since those fields interact with each other. But we're also trying to unify the strong force in with that. And that's not entirely figured out, I don't think, although there are interactions between strong fields with, and stuff, I think. So I guess the strong fields would be the gluon fields, because gluons are the mediators of the strong force. And so we typically call them the gluon fields. But I think there are interactions there, but I'm not sure if we figured it all out yet. And so I guess the broadest, simplest answer to your question is no, they're not completely independent. I'm just not entirely sure how the dependence works. Marino wants to know, what does it mean when a science explanation is wrong, not just in practice, but in principle? What's the difference? Ooh. That's a tough nuance. Man, I think that there's certainly a line there, right? Because, I mean, there are lots of things that are wrong in principle that work fine in practice. Like, assuming the earth is flat is probably the most obvious example there, right? If the range over which you're doing your experiment does not exceed 2 miles or so, 3 miles maybe, uh, I'd say 2 miles, give it some buffer there. So if it doesn't exceed like 2 miles or something, assuming flatness is fine, practically speaking, uh, it's fundamentally wrong because the earth is curved, but it works. I mean, it's what you do in intro physics all the time when you're doing, free fall problems or projectile problems. You assume the ground is flat. It's a very common assumption, even though it isn't flat. And so I think you can get away with a lot of things in practice that you can't in principle. And so when it comes to wrongness, I guess it just depends on what question you're asking. It's hard to draw the line, though. All right. Yeah. So, I mean, if you're talking generators on the wheels for perpetual motion, no, that's not how that works. But I mean, even if you did that, like, you're still not going to get all the energy back that you used, right? There's always going to be some loss and efficiency and all that stuff. So, like, even if you manage to get something like that to work, it's not like you can drive forever. You've also got back EMF and things like a motor and a generator that you're trying to turn, which resists you, and so it actually slows down the car, and it's complicated. Does the Pauli exclusion principle do its repelling if only one parameter of info is matched? The Pauli exclusion principle is a purely mechanical phenomenon that can manifest as a repulsion on large scales. Right. I don't know that on the particle scale, if you could look at it and be like, oh yeah, that's repulsive. It's not really repulsive per se, but it does look that way classically. And this is something we actually use to, describe the equilibrium of things like white dwarf stars or neutron stars, which I am really excited to plan a video on this coming year. Because I know a lot about white dwarfs. But it's hard to call it a repulsion. I'm comfortable calling it an outward pressure because pressure is certainly because pressure is a classical thing, but is a large scale thing. But when you start to get to the microscopic scale, you start having to use words like repelling, and I'm not entirely comfortable using that word for the Pauli exclusion principle. But I guess the question is, could a spin up electron and a spin down electron overlap 100% of their clouds in the same exact place? Um, yeah. So okay. So here's the Pauli exclusion principle says that no two fermions, electrons are examples of fermions, no two fermions can exist in exactly the same quantum state at exactly the same time. And so what that does is it allows two electrons to exist in an atomic orbital at the same time. And I say two because you can have one that's spin up and one that's spin down. And if they have opposite spins, then they're not in exactly the same quantum state. They are in slightly different quantum states. But because there's only two spin options, you can only fit two into the other properties. Right? So the spin allows two electrons to be in there, allows them to be different enough to have the same values for their other properties. But I don't know. Saying their electron clouds overlap. Again, I feel like that visual is a little too classical for what's happening, right? It's really best to think of quantum states as abstract. I mean, we love to have visuals and we love to have like some kind of visual context that we can put things in, but you can't always do that with quantum mechanics, unfortunately. When antimatter and matter annihilate, does it only happen for like particles? Or can any antimatter and matter annihilate? No, it has to be the same, right? Because in a matter antimatter reaction is actually the reason it's special is because it's a reaction that takes place in the same quantum field between two disturbances, two particles in that field. Right? So instead of two fields interacting with each other, it's two particles or disturbances in the same field interacting with each other. And so in order for an electron to have a matter-antimatter annihilation, it has to interact with a positron. It has to be a positron because it has to be a particle in the same quantum field. That's what makes it a matter-antimatter annihilation. All right, very active chat. All right, let's see. Got time for maybe one question or two if it's quick. Should gravity still be considered a fundamental force, or is it settled that it's just the effective curved space-time? The curved space-time model that we have is the best one we've got. No one's ever been able to bring it into quantum field theory. We want there to be a graviton and a graviton field, but it just doesn't seem to work. And so it's kind of this outlier, and it still sits out there, and so I would say that the curved space-time idea is the best we've got, but I would not call it settled, right? There are lots of physicists that are still uncomfortable that gravity is this model that's outside of quantum mechanics. And because it's outside and they don't cooperate very well, we know that there's something wrong. We're missing something. And so it is definitely not settled. All right, so I think as far as questions go, I think that'll be it for now, and we'll save some of these for next time for the end of January. But there's some talk in here about the Discord server. Just like to remind everyone, if you haven't noticed, the Science Asylum Patreon has Discord server access. I can't figure out how to get it to work for YouTube members, at least not safely. And so that's kind of a bummer, but anyone who is pledging on Patreon does have access to the Discord server. I go in there periodically. It is kind of a ghost town at the moment. I don't know if that's because people don't know about it or no one wants to talk to each other or whatever, but it is a place that's available for you to talk to each other if you have something more to say and you would like to interact with each other without necessarily involving me. You can, share links and have conversations. And like I said, I pop in there occasionally, but when things get really hectic, I don't necessarily do that. But on that note, this was a very exciting stream. We got some new questions that I've never gotten before in these, so that was nice. And the next stream should happen at the end of January. That'll be January 29th, I think, is the last Saturday. But as usual, I'll post an announcement. And hopefully all of you have a great rest of your day, great holidays coming up, and I'll see you next month. So, have a good one.